Okay. Ah, we're missing Alexei. There he is. You there, Alexei?
Yeah, sorry, I forgot to
that was interesting as well. I had for you, I had to click admit, but everyone else was just able to join.
Maybe I'm not signed in or some other weird stuff. Zoom is weird in terms of UX, to be honest. It's funky.
I suppose it is. Okay, well, so I don't know if anyone is watching the recording that is not on our team. What I wanted to do is we had spent some time, maybe 2 weeks or so in January, to look at like how we could possibly improve performance when exporting application metrics from the GitLab Rails monolith. And one idea was to, because we do this in Ruby currently, and we basically went through a process where first it was exported and to some extent it still is exported from an in-process daemon thread. So it just runs, it kind of shares CPU time with like the worker it runs in. That is still the case for Puma. We actually moved this into a separate Ruby process on Sidekick already, at least for SaaS, not for self-managed. Yeah. And yeah, the idea was to see, can we make this faster and more memory efficient if we just do not write it in Ruby, but see how fast it can be in Golang, because that's something we've been using a lot at the company over the past couple of years, and we had some really successful projects coming out of this, like Italy and Workhorse. So that's kind of where this all came from. And so it was, and to some extent still is, an experiment. It's not an official project yet. So I thought maybe it would make sense to start with something like talking a little bit about how this works currently in general, like outside of the new system, because I'm not sure how familiar you are with it, like the Prometheus client that we use and how it works exactly. Yeah, because I think that let's talk about this for a few minutes, because I think this will be useful before we dive into the code. So I'm going to share my screen. Cross my fingers that this works. Let's see here. Can you see my calendar now?
Yep.
Okay, good. So this is working then. All right. So I just scribbled something super quickly, so it's a bit crude. But can you read this? Is this big enough? Okay, this is a super high-level view of how it currently works. Basically, what's happening is we have workers here on the left, here. And it doesn't matter if that's a Puma worker or a Sidekick worker. Each of these things here is a separate process, right? So basically, so this whole thing here, this runs all on the same pod, right, in production, like all of this. And then we have worker processes. Sometimes they fork from a primary, not always. In the case of Sidekick, they don't. But that's the current approach. And then we have, at least with Sidekick now, a separate exporter process which runs alongside these worker processes. So the question then is, how do they communicate, right? So we're talking about exporting metrics to Prometheus here. So the question then is, how can one process read the metrics emitted from a separate process? So this is where it gets interesting. So basically, and we've been doing this for a long time, these worker processes here, they use a library called prometheus-client-mmap, which I'm not totally sure if this came out of GitLab. It has been around for a long time. But basically what this does is it is a solution to collect metrics in a multi-process Ruby environment, like a preform server, or multiple Sidekick workers that you run on the same machine. The reason this even exists is because Prometheus, when it was first created, it wasn't really designed with multiple processes kind of serving the same workloads, right? Because usually you scale out horizontally via threads. So you have one process and you share memory, right? This you can't do, or not as easily if you have multiple processes. And all of these workers, they produce their own metrics. And but they might be serving the same kind of workload, right? So they're kind of like a logical entity that belongs together, right? If you think of Puma, you don't really care like which worker serves a particular request. You're really interested in the aggregation of all of these metrics for a single node, right? Whether it's 2, 4, or 20 Puma workers running on this doesn't really matter. You're interested in the aggregate of all of these samples collected. So you need a mechanism in which each of these workers in their own process sample the data you want to track, whatever that might be. And you need to do it in a way where you can aggregate it so that it is exposed basically as one single logical set of metrics. So this is kind of the tricky bit. And Prometheus for a long time did not come with any solution for this out of the box. And I believe this is when prometheus-client-mmap was conceived. And there's other solutions to this. I researched this a bit. There's a solution as well that just uses plain files where you just write them to disk and then you read them from disk. And apparently that's actually faster than you would expect. But I don't think it was fast enough for GitLab. So we use prometheus-client-mmap. And what this does is it creates a bunch of files on disk. And I can show you, it might be easier to see in practice how they are structured, but they're basically structured by the metric type, like a counter or a gauge or a histogram, plus the aggregation they use. And I can show you an example of this later. And what these workers do is they map these files into memory using mmap. This has the advantage that it's very fast, because if you have a process that samples a metric, you basically just write to memory address. And then you let the kernel handle let the kernel handle writing these pages back to the file on disk. So this is kind of nice, because then the workers they don't need to know even that there's like files on disk. They just use the data structure in memory basically, so that of course like it's all behind like a nice convenient Ruby interface, but it uses a C extension under the hood. So you really just like, you increment a counter, you attach your labels, and this is written to memory, and then eventually the kernel flushes this back to a disk. So that's kind of the client like side of it. So this is basically all like the client side of it, which is sampling metrics, right? And then we need to serve them. So in which case that's kind of simpler, right? So we need to just walk over these files. It's not actually that simple, but basically, we just need to read these files back into this thing here, which is a different process, and then just serve it to the Prometheus scraper up here. And that's just an ordinary HTTP request. So in the previous model, this would go straight to these workers, right? We would like elect one of these to be the exporting process. And in Sidekick, it was random. There was actually a race between the worker processes that we started. And whoever would first connect, like allocate the port over which we serve metrics, that would be the winner. And that was then the designated server process for Prometheus. Then we changed it to a more stable approach where we just always let cyclic 0. So the first one that we start handle this. And in Puma, it's always the primary. So from which we fork, which serves these metrics. So that's the old approach. And this is the approach you want to move to. So one tricky bit here is that you need to understand a little bit like how these files are structured in here, right? These metrics files that are written to disk, they're just binary, right? So they are not in the format that Prometheus calls an exposition format. So Prometheus has this concept called an exposition format, which is just a way to render metrics to Prometheus in a way that it understands, right? Because the scraper, of course, needs to expect like them to come like in a certain form of serialization here. This is just a binary format. So we need to parse this first. And because it is per metric type and often per PID even, so these workers will have separate files, we need to aggregate these metrics. So we need to import them in this thing here, the exporter, and merge all these metrics together before we serve them to Prometheus. Otherwise, you would just serve only a subset of them. right? So this is kind of the major challenge behind this approach, that we have these disparate set of samples coming out of here, and then they just get thrown into these files, and so somewhere they need to be brought together again. Does that make sense so far?
Yes.
Good. You can just interject with questions if you have any. So if you look at this on disk, let's see here. Yeah, so if we just look at, we have this, so this is, or maybe I should say first, so this project that we're gonna look at, it lives in my own user account. For now, there's no documentation. I haven't gotten around to documenting this thing yet, but this is where it lives. And I have a bunch of test data in here. And I'm going to show you in a second how I went about this, but just for you to get an idea as well, how this looks like. If you look at, I have a couple, this is actually data we pulled from a production Puma pod. And this is how prometheus-client-mmap writes these files. So they are called .db. It's just a random extension. It's not, I don't think there's even a spec for this format. I looked, it's like very lightly documented on the project website. I just reverse engineered this by looking at the C implementation. So if you have, it's just a gem, right? So you can, so prometheus-client-mmap, if you look at this X folder here, you have all of the files that are responsible for, this is the implementation for the mmapped value implementation for a Prometheus metric. So here you can see then how it, there's like a parser. So here you can look at like how it's implemented and like how it reads this file. And the way it's structured is, you can see it is structured by metric type. And then what the library calls a PID, and this is very confusing because this is not, or not necessarily a Linux process ID. It's just really like a symbolic name you give to something. And this is to keep these stable, because if you have like 7, or in this case, 6 Puma workers, if one of them dies and is restarted, you don't really care that it gets a new PID assigned by the Linux kernel, right? So you still want it to be, you know, worker N out of your 6 workers. So you can give these like symbolic names. Right, so it's metric type, a PID, and then there's this another extension, which is if this is just it's just a number that's incremented if you should happen, if you should create a file by the same name that already exists. It's just so that you don't accidentally overwrite data. So you can disregard this postfix here. There's one special case where for gauges, there's also an aggregation in here called all lifesum or max. And the reason for this is that if you think about it, if you aggregate data, metrics in this case, across different processes, you need to ask yourself, well, how do you aggregate them, right? With what is your aggregation function? And if you think of a counter, let's say you have a counter for HTTP requests, right? So the number of successful HTTP gets or something like that. Then clearly the aggregation you want is a sum, right? Because you have 5 workers and each of them serve a portion of the traffic, but what you're interested in is the total number of requests served from this pod or machine, right? So what you have to do is you have to go through all of these files and sum them up, right? So each sample with the appropriate label set that is logically the same, it will have a different value attached, right? So you can just sum these up. And for histograms and summaries, it's similar. And the reason you want the sum is, well, it's a counter, right? It always goes up. So you're kind of looking for the total here. For gauges, it's a bit different, right? Because gauges can go up and down. So then the question is, well, how do you aggregate them, right? Because let's say you have a gauge for, I don't know, what's a good example? A gauge for, well, memory use, right? So RSS consumed or something like that. So that can go up and down, it fluctuates, right? So it doesn't always go up. So then the question is, well, if you have 6 processes that all track different RSS values because they're different processes, but which one are you going to report if you aggregate this, right? So you need to tell it, you need to tell Prometheus-client-mmap how you would want to aggregate these before you export them. And there's these three strategies. You can say all, which means they will all be retained as individual samples. And the way Prometheus-client-mmap handles this is by actually including the PID, this, Puma 0, Puma 1, etc., as the PID label in the final aggregate sample set, so that these are all discrete entries. So basically, in this scenario, you would get one entry, like one metric entry for each process. And that's actually a good example because this is definitely what you want, right? You want to, like, RSS is very process specific, right? So for an RSS gauge, it makes perfect sense to use the all aggregation to preserve all of these. And that's actually the default as well. If you create a gauge using the Prometheus-client-mmap interfaces, the default is to preserve each sample. You can also sum them up. I don't know what a good use case for this is, but if you want to do that, you can do that. Or you can do something like you want the max, right? You can also say, well, they all track something individually, or the min as well. I don't have an example for min. There's also, of course, a fourth one, which is min. But you can say then, like, okay, so these all do kind of serve the same workloads, but I'm really only ever interested in the highest value of something. And like one case I've seen is, one use case is, I think we track the GitLab version, the application version somewhere, and we use a max gauge for that. So because we want, because if you like roll out, I guess it's because if you do like a rolling deploy or something and some older workers are still around, you're not interested in like the older version, you always want to get the newest one, right? So that could be one example. Right, so that's, so this is the data we need to consume, right? So this is what we need to read and process in this thing here. Does that make sense so far? Any questions?
How do you say on client that you want to use max?
Yeah, good question. So you can just, GitLab is open, I do. So if you just search for, a gauge, create a new gauge somewhere, let's see, here. You can tell it here. It's just a parameter.
Yes.
This is our wrapper around the Prometheus-client-mmap. It's in Prometheus RB Prometheus. Sorry, here. So these are just helpers around this, and I believe, it's called multi-process mode. Is what the library calls this as well, and you can just pass it here.
Thanks.
Okay, so let's look at the exporter then. So these are kind of the nodes I wanted to go through. If we don't get to all of it, that's fine. So the basic, I'm going to super briefly touch like how it's structured. It's super simple, actually. So I have, let's start actually from the top. So we have two entry points, the main or go files here. One is, and that's how I started, is a simple CLI wrapper. I did not set out to write an HTTP server. Like the first thing I did was I wanted to have something that's super easy to use, and I can just run it on the command line, write a bunch of tests for it and see if it works. So one of the first things I did was to just write a simple CLI app that calls directly into the implementation, and you can give it, you just can give it a target directory to these DB files, and it would then call the implementation and serialize them to stand it out. Pretty simple. A bit later, I added a server that's super easy to do in Go, like ridiculously easy. You basically just need a handle func, which is the it's like this lambda you pass here. So it's just you pass, it's a higher order function, right? So you give it another function, and that's your endpoint handler, right? So it's kind of like a Sinatra mount point or like a Rails root, like very similar. And then you just do this blocking call here, listen and serve, and you give it a port. That's it. So off you go. Pretty nice. I really like this. And the actual implementation So one of my kind of design goals with this was that to very early on, I didn't want this project to be just about serving this particular set of data, because I wanted it, I hope that eventually we might be able to use this as a drop-in replacement for GitLab exporter as well. Because you remember we looked at this quite a bit, as part of the 2 GB effort and stuff. We would kind of all like for this to go away, actually. And so my idea was, well, if like what I like about GitLab exporter is actually its design. It's like very flexible. So it has this concept of a probe. So it very clearly separates the responsibilities between being a server to Prometheus to fulfill a scraper request over an HTTP server, and the responsibility of probing for metrics data, right? So it's very nice, actually. It has a very simple but clean design. And I borrowed this design. So the idea here is that I only have one probe, so it's a bit of a premature abstraction, but the idea is that we have a probe, which is a very simple type. It basically, so this is the probe type. Oops. And all it does is it has a function called probe, and it returns either an array of a metric group or an error. And there's an asynchronous version of this as well, which means you can publish these results into a channel, but it does the same thing. So it's a very simple interface that you need to implement, and you could do anything, right? It's not just probing into an mmap directory. It could probe into a Redis instance or something, or a database, and pull out metrics from there. As long as it's able to somewhat translate this to this metric group type, then it should work. So that's the first bit, and this is what we were calling here in the server or the CLI, whatever. So we create a new probe. This is currently hard-coded to use mmapdb, but you can imagine we can just give it a config file, like a GitLab exporter, like a YAML or whatever, where you tell it, or just provide it in the environment or on the command line, just say, probe like X, Y, and Z, and then it would map this to, an mmapdb probe or Redis probe or whatever. So you just call probe, and then this result you feed into a renderer. So render is also very simple. We only have, again, only one implementation of this, but currently I need to find that here. So currently there's, again, like a synchronous and an asynchronous version of this. So the synchronous one, you give it the result of a probe, right? Which is this list of metric groups, and you give it a writer. So it needs to turn it into, so it's called render text because this is the text exposition format. This is what you see if you call any of these metrics endpoints, right? It's the line by line output where you just have, like sample equals value, basically. So this is the formal grammar for it, very simple. And there's an asynchronous version of this where it operates on a channel, but that shouldn't concern us for the moment. So it's actually quite simple in terms of the overall design. And then the next thing I did was I wanted to, I didn't really know what I was doing when I started this, right? Because I hadn't really worked with prometheus-client-mmap and this data format at that level. So what I did was I actually I added this folder. That was one of the first things I did, which actually uses the Ruby client to render a given directory or a given file. This renders a full directory, and this renders a single file, which calls into this C implementation in Ruby, in prometheus-client-mmap, so that I could compare the output, right? So that I could have some kind of like parity test. So I added these acceptance tests here. These are Go tests that really just do, you can see in each step here, we render with the Ruby client implementation first, and then we render with this implementation, and then we compare the results. So this was kind of my, like, so that I don't like swerve too much off the road, right? While writing this, because I wanted it to be correct first, of course. So I wanted to get to a working solution very quickly, which was then very inefficient, and then go from there, kind of, make it work first and then make it fast. Yeah, that's actually all there is. So So before we look at the improvements, if you want to build this thing, just check it out. You can just say make, and then it builds both the CLI and the server binaries, right? And then you can just run them like, so we have bin export CLI, I believe, yeah. And then you can give it a, you can give it any directory that contains these .db files and call it, and we'll render it. And you can see here we have, what was that? 32,000 samples. So I don't actually know if that's super big. It was, I think, 40 megabyte on disk or something. It's certainly not small. So it's probably on the heavier end of a workload to process. So it was a good test case to look at. So my idea was we can go back to an older commit. So I picked out a few older commits to see what it used to do, because now it's quite fast, right? So it wasn't always quite fast. So if we go to this commit, the problem really is that, of course, in older commits, I didn't have some of the tools I wanted to use, but then we can see how it compares, right? So this should still work. Yep, so it still works, that's good. You could already tell, I don't know if you could tell, but you can tell that it's a lot slower, right? So my first challenge was, this is to commit like shortly after the first green build, right? I was first working towards a green build. And here's how I went about it. So I noticed it was slow. It was, I think, so in the benchmarks, I can show you that later as well. We have benchmarks as well, but I think in the benchmarks, it was actually slower than the Ruby implementation. Or maybe it was the other way around, I forgot. But like either in the benchmarks or on the command line, one of them was slower than the Ruby implementation. And that was really annoying, of course, right? Because I spent so much time on this. And then I was hoping, oh man, it must be faster, right? If you write it in Go. But turns out that it's not that easy. It's not that simple because Go is a garbage collecting language, and there's a lot of stuff you can do wrong, right? So that obviously your app is gonna still be slow. So personally, and this is not specific to this project, the first thing I always do is I do this like top-down kind of style of profiling where I just look at these really at the headline figures and see if anything stands out. So I have this handy script here, time sh, which is really just I don't know what, if you're on macOS, I don't know what time is on your system, because I realized that on Linux, there's a built-in call time, and then there's a tool called time, user bin time, which is way more powerful actually, and it has a couple of really useful flags you can set to see the output. So if we run this, see what we can see. Right, so I find this very helpful, right? So it gives you the total elapsed time, that's kind of the wall time, right? How long it ran. It will tell you how much CPU it used, so 1.09 CPUs. You can see there's a little bit of concurrency here, probably because of the garbage collector, because I believe in Go, the garbage collector is actually concurrent, unlike in Ruby. And then it will tell you, well, how much of that was spent in user space, kernel space, and memory used. And these are context switches, voluntary context switches, and involuntary context switches. I'm actually like surprised that, oh, it actually fluctuates quite a bit. So because I do remember like sometimes these were super high. I think that was one of the first, so I don't know why it fluctuates so much, but I do remember seeing that it fluctuated a lot. Sorry, it was super high, even if it fluctuates a lot. So I was wondering why is it doing so many voluntary context switches? So if you look this up, I think it's even in the time man page, it will tell you this is the number of times the threads or the test is suspended because, well, voluntarily, because it's waiting for something else to happen, which is usually a red flag, because it's something, it means like your application can't do any work because it's waiting for the kernel to do something, most likely. And the most obvious thing there is I/O, right? So the next thing I did was I looked at strace. Are you familiar with strace at all? Yeah. Everyone? Okay. So just in a nutshell, strace calls tracks system calls, and it's super versatile tool. So there's a billion ways you can invoke it, and it can give you very detailed outputs. But I find actually the most useful one is this very simple invocation. The C is count. What this does is it groups and ranks system calls by call type and tells you how often they were called, right? So it gives you this nice little summary, which takes a very long time. And well, you can see here, I think this actually also fluctuates a lot. Let's see if it fluctuates again. I also had cases where it took like a very long, it fluctuates, but it's still pretty bad. You can see here, so the top of Fender here is a system call called read, which was called 47,000 times, which basically means we had the more than once for every sample. That's not good, right? So we had 32,000 samples. So that's terrible. So this was like a dead giveaway. I mean, the read syscall, should be pretty obvious. That's for file IO, right? So it's waiting, or stream IO, could be any kind of IO, right? So it's waiting to read. So it's calling to the kernel to say, I need to read from this device, and I'm waiting until data is ready to be read. So that's also where the context switches come from, right? Because that's this voluntary suspension. It needs to wait for data to arrive. So that was my first hint, like that, okay, that was maybe not super efficient. And if you then look at what I had done, this is the code for parsing the DB file. I actually got to do a super quick detour because that might help to understand. I think I have a example somewhere. Yes. So if you look at the file, if I remember correctly, I thought I had documented it here somewhere. I need to do that still. Apparently I have. Maybe I did it later. So if I remember correctly, the way these DB files are laid out, you wouldn't be able to see it nicely if you just like cat them or something, because it's a binary file. I think it's like an 8-byte header, and of which I think 4 bytes are just padding, and then 4 bytes are the content length. It's so that's not the file length. That's the length, the data length, right? So how many bytes the actual sample data is in the file. So you need to skip this basically and parse this out, and then it goes straight into metrics. So then there is like basically, you know, an array. It's not an array, right? But it's a bunch of samples. So that and it's also not line delimited or anything, right? But you can think of it logically like this. So that's like where all the samples are. So these are the actual samples, and the way they are encoded is I think the first field, I forgot the order, but I think the first, yeah. So the first 4 bytes are the sample length again. I think there was padding again as well somewhere to 8-byte. There might be 4-byte padding. So again, you need to parse out a number to know how far you need to read, right? And then you have the actual data, which is, well, it's this long, right? So it will tell you in there how long it is, but it's variable length. And the actual sample data looks like this. It's actually a JSON array. So I was really surprised to find that when I was like going through the prometheus-client-mmap source code. It's basically a JSON array. So, and it's an array of, so that's a text string basically, right? So it has the metric name, and then I call it child metric name. I don't know, or submetric. This is a bit of a hack because Prometheus does not really support histograms. So what Prometheus does with histograms is it creates actually 3 metrics for one histogram metrics, a counter or 2 counters, like one for the observation count, then a sum counter to sum up all the observations, and the buckets, right? So so except for histograms and maybe summaries, I haven't really worked with summaries, but for all other metrics, this is always the same. So that this is actually something where I thought, oh, that could probably be more efficient, right, on disk as well, because for most samples, this is kind of duplication. But then you have these 2 like nested arrays, which are tuple, right? You need to zip them up. The label names and label values, right? So you have label A, like, I don't know, like HTTP status or something, and then this would be, 200, and then you have HTTP method something, and it would be get, a string here. So that's how it looks like. And that's pretty much it. And then it's just a repetition of like these things, n times over. And that's what you need to parse. All right, does that make sense? Right, so if you then go to the parsing function, which was here. So if you look at this, you can see there's like a lot of reads happening, right? So we open the file and then we read out the header. So the length of the actual metric data in the file. That's a read. Then we skip padding, which is a seek. So that produces a system call. And then if in each sample that we read, we do another read, for the sample length and so forth. And then we read the actual. So you can see like there's all of these individual reads going on here. So that's not good. So that was the first thing we had to optimize away. And there's actually a nice way to see this as well. So something else I looked at was profiles. Here's another cool feature. If you go to bench test, Go has a built-in support for running benchmarks. They look like tests, and you just say benchmark underscore, and then that gives you a benchmark. You can see here, run benchmark. And you can configure these, and you can also, when you run them, you can tell Go to dump a CPU or a memory profile, or both. So if you run them like this, so now runs the benchmark that I specified here, and then you get these profiles. CPU prof and memprof, right? And so this you can just throw at speed scope, which I think I had open somewhere here. I don't think that's the correct one though. If you go to CPU prof, I always use left heavy. I find it so useful because then you see how it stacks up, right? So this is like what I was looking at. You can see here almost all the time is spent in probe, specifically parse files. Takes up a lot of time, right? And you can see a couple interesting things here. So first of all, it's these reads, they sum up to a lot of time. A lot of them coming out of this binary read, but also just a normal file reads. And that was the first thing that stood out. So yeah, reducing reads would be a good idea. But also another interesting thing was how long it took to decode this JSON key, right? Like this thing here that I mentioned. This thing here, this was super slow. So I was wondering, like, why is it so slow? And I just Googled, Go JSON decoder, and it turns out this thing uses reflection, right? So if you create this JSON decoder and you give it an array, it's also due to the problem. It uses reflection is one thing. The problem also here is this is like a mixed type array, right? So we have, these are all strings, they're just the label names, but the label value can be anything, right? So this could be a number, or it could be a string, right? So there was a bit of a problem, and also it doesn't really know by default how to like parse this nested array, because it doesn't really know what this is, right? It could be because this could just be another JSON object, for instance, right? So you need to pass it the any type, which is this interface thing here. And then it needs to use reflection to figure out what the actual type is. And that's very expensive. So one of the things I did was I did not use the JSON library, but I just, because this string is like so well understood, like the structure, I just did like a manual like string routine, just like splits up the string, and Camille made this more performant in the end as well. So those were the two major changes. So reduce the read syscalls and buffer the file and memory, and optimize this entry parser. There was also a smaller thing. I think this had to do with, oh yeah. So another mistake I did, because I'm not very familiar with the Go standard library and all of that. and the performance anti-patterns. So this was very expensive. So I was basically I had a, this is the rendering routine, right? So I was basically walking over the samples and appending, I kept growing this like lines slice. So which means every time you run out of capacity, Go it will extend it automatically, right? If you call append. So that was very inefficient. So what I did was I used the string builder, which was faster. Turns out this was still slow, and I'm going to show you Camille's solution to this, which made it even faster. But we'll get there. So these were the three things that stood out to me. So those were the first optimizations I did, so which basically led to this commit. Oh yeah, did I make changes? Oh, I did. Yeah, of course. I documented this stuff in there. Just get rid of that. Build that again. So I kind of forgot what the timing was, but let's just run it again. See what happens. Yeah, this is a lot faster already. Context switches are much lower as well. I think about cut in half. Yeah, so this used to be like 4,000 plus, at least 3,000 plus. So that's more than cut in half. And it's much faster as well. Remember, it took like over a second sometimes before we called it earlier. And you can see it in strace as well. Yeah, see, they all disappeared. All of these reads are gone now. Maybe one thing to show here as well, which I don't think I did, is so this was maybe the most impactful thing, right? Because previously I would just have all of these individual reads, and then instead you can just say read full, and this reads it all into memory. So, and this is a typical time-space trade-off, right? So I made it faster, but I made it less memory efficient. Well, that's not the wrong word. I made it use more memory, right? Because now I read every file into memory in full. Obviously, that makes it faster to interact with that content, but because it's just buffered in memory. But it also means, I think this actually led to consuming a bit more memory. I'm not totally sure, or was maybe about the same. Any questions so far? Oh, actually, one more. I think this is also interesting because remember in the profile, there was something about, where was that? Yeah, was it in sort? Might have been this one. Forgot which one it was, but there was something else stood out to me, and I saw, because you can tell as well, like a big chunk as well is spent in GC, right? So GC background mark worker. So this is always the dead giveaway that you're just creating too many objects, right? So the GC has too much work to do. So you should look for improvements where you create a lot of temporary objects in loops, maybe stuff like that. And I noticed that I was doing, I had this innocent function here, which you need to implement to do a sort. So the way Go approaches interface is a little bit like type classes, where just by virtue of defining a bunch of methods, you implicitly implement interface, right? So it's not explicit. So if you want to be like a sortable or whatever it's called, if you need an array that's sortable because it contains your own type, you need to define 3 methods on this type, which is less swap and len for length. So and here what I did was to compare 2 samples, whether they were ordered, right? What the order was between them. I did this like innocent string concatenation here, but of course I was calling this like, I don't know, like tens of thousands of times. So it created all of these temporary strings in here. And so the garbage collector had a lot of work to do. So I optimized this by not creating any temporary objects here anymore. All right, I think I checked this out already. Yeah. So the next big thing that was on my mind was up until that point, everything had to be synchronous, right? So if you look at the probe interface, how it looked back then, it was much simpler than it is now, right? So you call probe, takes no arguments, and it returns a sample slice or an error. So it's a synchronous interface, right? But I mean, I knew this like going into this, that this is a parallel problem, but I wanted to start simple first, right? And the reason it's a parallel problem is because we have all of these files that are not necessarily related, right? I mean, we can parse them in parallel, then we can merge them together before we render. So I think there was a ton of opportunity for making this asynchronous. So I had to introduce an asynchronous interface first, and so that we can then use Go routines to actually run it in parallel and then zip these results together, basically. So that was the next step, which that was, I mean, pretty straightforward, right? Because I had already I had a working implementation, and then making it asynchronous wasn't that hard. This has changed from back then again, but basically the idea is that you need a way for your Go routines to communicate, and not the only, but one way, or I guess maybe the most idiomatic way, is to use a Go channel. So I think we're going to definitely overrun, actually. Is that okay with you? If you want to talk about Camille's stuff as well, we're going to overrun. I can ask again at 12. So you make a channel, and it's a communications channel. So there's like a buffered and an unbuffered version. But the idea is basically that you pass a reference to this channel around, and then you have these different Go routines that pull from this channel or push things into it, right? So you can create a Go routine, and Go will internally schedule this on internal thread pool. So this is not equivalent to a thread. It's just kind of its unit of concurrency, or whatever you want to call it. But it will run concurrently to the caller thread. So all I did was to instead return the value synchronously, just put it on that channel, and then have the renderer listen on this channel. So as soon as a set of samples would arrive, we could render it out, right? There were a bunch of complications for this, because the renderer, you want it to be ordered. Otherwise, your samples are going to be all over the place. So this was trickier than it sounds, but that's kind of what it boils down to. Yeah, so there's really not much else to say here. I think, yeah, let's not get into too much detail here, but you can see how that performed. I think if I remember correctly, there wasn't a huge difference when running it on the command line. I think, look, it like even got a little slower. And this is like one thing where I realized as well, I had to start building the server, because the problem is, if you profile something like this, you will have a lot of skew in there, right? Because you also profile the time it takes for the Go runtime to start. But that's a cost you only pay once, and then it amortizes, right? Because the server is a long-lived thing. So so I was starting to hit like limitations with this, instead, I think we should have the server already here. Yeah. So what you can do is you can, so you can run the server. You can give it a target directory as well, and you can just use AB, for instance, to profile that. And this actually turned out to be faster. So once you get rid of the startup cost, and let it run hot as well, I guess. So over, what is this, 100 requests, I think it's sending now. This was actually a nice performance improvement as well. Still not super fast. I don't know, it's taking so long now, actually. All right. So still, yeah, not super fast, but I can see like definitely faster than when just running it once, like on the command line. All right. So that was basically where I stopped working on it, and then I paired with Camille for a little bit, and we made some changes together, but they didn't really improve. I think they made memory use a bit worse and CPU time a bit better. So like Camille sat down as well and looked at a bunch of additional optimizations. I picked out some of them that I thought might be the most interesting ones, but I think Camille is not here, right? So if you have any detailed questions, ask Camille. So he's probably the best person to talk about it. But there were some themes as well, I think, to the improvements he made. One was around buffering and like making sure, basically reducing the number of times we have to allocate new memory, be that because maybe objects are too short-lived, or maybe they're not correctly sized, right? So that because if you use slices a lot, for instance, especially if you add to them in a loop, every now and then the Go memory manager will have to grow that slice because it can't hold the additional data anymore, right? So this can be costly. So a lot of Camille's optimizations were focusing around using a heuristic just by looking at the numbers of like what is a good initial size for this list of things and samples in this case, so that we can avoid having to resize slices, for instance. Also, so yeah, he looked at what could be like it's basically like it's a bit like finger in the air, right? But he looked at the data and said like 200 samples per file on average is what we see. So we now buffer sample data. We create a buffer that will hold 200 samples initially, which might be too big for some files, but it works in a lot of cases. That avoids memory allocations. Then interesting thing as well is that we had used a read call to skip padding, and that sounds like innocent, right? If you just say something like copy n or just read 4 bytes and just throw them away or something, but it's still a read, right? So it's costly. So there's this handy function called this is a super handy package. Like if you do anything with like processing streams, look at buff.io, they have a lot of very efficient helpers in there. So and there's this useful discard function where you do not pay this price. So if you look at the parser now, whenever we encounter padding, for instance, let's see, discard. Oh, where is it? Oh,
I think you're on the late
I'm on an older commit now. Yeah, so I should probably just go back to main actually, because I'm not going to check out every single one of Camille's commits. He like went back and forth a bit between optimizations. So if you look at his commit history, he actually undid some changes he did in between. So I think it's easier to just look at the final thing. So yeah, so discard. Oh, where is it? Oh, I can't find it anymore. That's weird. I guess we moved it here. Okay. No, that's the benchmark. I don't know where that went. Maybe he took it out again from the file. Oh, I think I know why. Yes. So that was actually one of the intermediate commits, which made a lot of sense. But we now use an approach where we just have this pre-allocated byte array. So we can actually skip around in the byte array. So we don't actually need to discard. But generally, I think it's still good advice. Like if you operate with a stream and need to efficiently ignore a certain byte range, you can use discard reader. But actually, we didn't end up using it because he just basically used an offset now. Next one was, yeah, this was a really big one that happened over a number of commits. In the initial code, I defined this sample data structure. I had a bunch of fields on it that basically did not change per file, right? Like the metric name sorry, not the metric name, the metric type and the metric aggregation, as I showed you in this file list, right? It's going to be the same for every sample. And initially, for convenience, I had stored it on the sample type. So if you have 30,000 samples, you basically duplicate it 32,000 times, right? So so he did a couple of improvements around removing this duplication and moving this out into a shared, actually 2 things. So one was around delaying, like when we need to access this data. I think that's this commit where he actually delayed this until we render, I believe, so that we do not have to hold on to it while parsing files and merging samples. So that reduces the amount of memory used until we need to render, which is when we actually need these missing fields. So that was the first one. Yeah, you can see here, this is so he removed, so we now only keep key, type, PID, and value, and he removed the label slice. and the name. So that was the first one. And the second one was to introduce a shared data structure that keeps around the file metadata a little bit longer. I had thrown this all out after parsing a file, and it was then kept in the sample data structure. And again, this shrunk the sample, the amount of memory we need to store in individual samples. So see, we could now, so sample is now really just a key and a value, so super small. And type and PID, because again, it doesn't change, has moved to a shared structure, which we don't need to allocate as often as we allocate a sample, right? Because we have 30,000 instances of this thing here. And this is only per, I think this is per file, I think. So much less memory used. So this was very impactful as well. This was also quite impactful, buffer writes in the renderer. So I mentioned earlier how I went from using a slice of strings that I appended to IO write string, right? Turns out that write string is also not super efficient because it's unbuffered. There's another useful function in the buffer.io package called new writer size that you initialize with a size of like what you anticipate the amount of data might be you need to serve per render call. So if we go to, where's render text? Here. So this was another improvement. Again, I'm not too sure how Kimmel came up with these numbers. I guess looking at what is the average amount of the average data size we serve per request. So this will make sure that we buffer all of these string writes, and then, but before we render, we flush it all at once. So this was very effective as well. Right, this was another one I saw during profiling because remember I had tossed out the JSON parser and used a simple handwritten routine that would just like take this JSON array and just split the string around certain tokens and then just look at these 4 elements that it has individually, which was a lot faster than JSON, but it was still not as fast as it could be because the strings.split function is actually really expensive. So, and it still kept showing up a lot in the CPU profiles, and also it instantiates temporary objects again. So it also showed up in the memory profiles. So actually Camille completely rewrote the decoder with like a handwritten thing that again, it just basically walks the string. It's actually not that complicated. He basically just treats it as a single byte array. It's a key string, and just like walks it. He tries to find these these like tokens of interest, you know, like where does the array start, you know, where does it split, and he just like indexes into this byte array. There's like, I think it's called like strings.index off or something like that. Strings.index byte here. So you can just, you give it a character, a byte, right? And you can tell it, well, give me the index in that array. So he just finds, it's a bit more complicated, of course, but it's way faster. So that was quite impactful as well for both latencies and memory, because it doesn't need to allocate temporary objects, and it's fast enough. I mean, it's linear, right? So we need to probe into this array over and over, but these lists are super short, right? So these strings are fairly short unless we have a billion labels in a single sample. So it's still fast enough. Right, this was an interesting one as well. I don't know how much that saved us, but I thought it was interesting. So we had one remaining call to read, which this binary.read, which we used to read a bunch of bytes and turn them into the expected data type in memory, right? Particularly for the content length, right? So, and for the metric sample length, because you need to parse this to know how far you need to read. And we used binary.read for this, but instead, since we know the byte array, it's actually way faster if you directly, because we knew what the type should be, right? We just used the math function to do this directly, which saved another call to read. So that was pretty effective. Oh yeah, this was a fun one as well. I had added debug logging like in a bunch of places because it was super helpful. And that was actually quite expensive. So, and this like never disappeared from the profiles. I had guarded it with the call to, so this is only enabled if you call it with, so if you call the exporter, like maybe the CLI, and if you say debug equals 1, you get a bunch of, it's super slow now, yeah, right? You get, it basically logs like every single sample it encounters and how it aggregates it, which was super useful while building this, but it was very expensive. So he removed it in a bunch of places and made it a bit more efficient as well. So I thought that was a funny one. Yeah, and then this is a fun one as well, like Nicola and I already talked about it. I would have like never occurred to me, but we need to sort in several different places. We need to sort labels, the name value combinations, but we also we need to sort metrics into place because otherwise the render output is going to be all over the place. And if you look at how this text exposition format looks like, you need to group them together, the metric names, and then they have a comment on top with the metric type and description, like a help entry for every metric group. So you need to actually sort your output, especially if you do process it in parallel, right? And by default, I just used sort.sort, which I don't think it's even specified in Go what it uses internally. Sorts data. Fair enough. It makes one call to len, and then it's n log n. So that probably tells us it's a quick sort, and I'm pretty sure it's a quick sort. And a quick sort can be super efficient, but on very small lists as well. And we process these in chunks, right? We don't sort the final 32,000 element list. There can be cases where it's not that efficient, also because it needs to allocate memory. So Camille thought, we can just use a memory-less approach to sorting. So he used an insertion sort, which is a very simple way. It's kind of this thing where you think, back to university, they probably tell you never use this because it's not as efficient. Yeah. Anyway, so that's what he did. So it's basically like this idea where you walk the array and then you check, pairwise, is this element bigger, smaller than the other one, and then you swap positions around, which is in this case really beneficial because it saves you from memory allocations. And because the lists are fairly short that we have, the fact that it's maybe less efficient overall computationally, it's still in our use case actually the better solution. So I think that was a pretty cool idea.
That is quite cool. To be honest, like one small comment to this, I remember in C++ and STL, like quick sort was using insertion sort heuristics. So if the array is small, like less than 10, 15, 50 elements, it uses insertion sort because asymptotically n square is less for smaller numbers.
Right,
like,
that makes sense.
N log n is just an major, it requires a lot of constant is bigger or on quick sort to say so than on insertion sort.
Yeah, and like I think
cool
the n
idea.
I think the n in the first n in quick sort is because it needs to find a pivot as well, right? So that's also something where I would imagine for if you have a very short list, maybe that's just not necessary to do, right? You can just sort it in place. So I guess that was some of the thinking.
That's cool. Yeah. That's cool.
That's all I had. I can maybe super quickly, and then we can wrap it up. What I found super useful along the way, which I haven't shown you, is if you say Go tool, like Go comes with a bunch of built-in tools. One is pprof, which is the Go equivalent for gprof, which is a profiler. And you can give it a CPU profile or a memory profile. I prefer to look at CPU profiles in a flame graph, so I didn't use it much for that. But if I give it the memory profile, I forgot which one this is now. We pulled it earlier, right? So it has this top K function. You can say, give me the top 10 kind of offenders, right, of memory consumption. And oh yeah, this is, by the way, I remember now. This is how I found out about the inefficient less comparison and sample slice. Remember where I was allocating strings temporarily. And quickly, like how to read this is, so you can see this is a top down, right? So it's listed in descending order. So the worst offender is always at the top. So you start reading from the top. And what these columns mean is, so you have flat and flat percent. Flat means this is so it's a memory profile now, not a CPU profile, but so this is the amount of memory allocated in this function specifically. So in the body of this function, and not in any descendants that it might be calling, right? So that's what flat means. And then that's the percentage of the overall. You know, you have an overall, yeah. So 367 megabyte were allocated, right? And yeah, so it gives you these percentages as well. And then so sum is so you can see this always grows towards the bottom. So this is basically yeah, out of, so you can see it's only showing you, so this is saying the top 10 worst memory offenders or functions that use allocated memory account for 83% of the total use. So the total memory use was 438 megabyte, sorry. So 83% of those 438 megabyte were allocated by these 10 methods, okay? So, and the sum is then the extent to which this contributed to it, right? And it then goes, it's then additive, right? So these two account for 30% already, right? And you can see here, then 50% is spent by the first top four methods. So yeah, it kind of gives you an idea like where to look. Yeah, and then cumulative is it's like flat plus descendants, right? So I think in the case, you can see here in the case of less, it's the same because I don't call any other functions really. And well, I do a comparison, but it's not, this is a big difference, right? Because parse file calls a lot of other like subroutines. So here's a very big difference. You can see that in parse file, in the function body for parse file itself, we allocated only 60 megabytes, 61. But in all the stuff that it was calling, we also allocated memory, right? So this is including the 61, I believe. So 61 plus X, right? Anything that other functions that we call in there were contributing as well. So this is super useful to look at because it allows you to, yeah, like hone in on like the biggest offenders, I guess, where you spend memory. Other than this, I haven't used these tools so much because I just haven't worked with Golang that much, but this was immediately very helpful. Yeah, that's all I had. Any questions?
I have a small question. So
Yeah.
how stable were the results of running both benchmarks and all this kind of measurements? So
yeah.
Were they stable, or you need to apply some shenanigans, you know, to rerun this multiple times, even though they're already running in cycles, so in loop? So have you been able to iterate, you know, like make a change, run a benchmark, see the numbers, and it's clearly see the difference? So where there's some, you know, issues with this kind of iteration?
Yeah, so that's what I'm trying to show here. The Go benchmarks are quite stable. I mean, you always have fluctuations. I also don't have frequency scaling disabled right now. So you will always suffer from a little bit of frequency scaling as well, but you can turn it off. But even then you will have fluctuations, right? Also, I don't know, if something else is running in the background, you may want to turn this off. But overall, the Go benchmarks are quite stable, right? You can see here, this is fairly stable. What was not so stable, like anything related to tracing system calls, was not super stable. And one thing I never got to the bottom of, which is, make sure I precompile, recompile. So yeah, see, like now it doesn't appear. Like sometimes I got like a huge number of ZIC returns here, which is that signals the return from a signal handler, right? But it doesn't really tell you what it was. So even with some of like Camille's improvements, sometimes I would run it and then randomly it would like jump like to, oh yeah, here, now it did, see? So suddenly I have like 27,000 calls of RT-zic return. And that like led me down a bit of a rabbit hole, and I never got to the bottom of what this is. So if anyone knows, I'd love to know, because I couldn't figure it out. Yeah, maybe I would have to inspect exactly, because this is just grouping by the syscall type, right? I would actually have to look at what the system call was, right, that it was returning from. So I would actually have to trace them all here, and then trace them often enough for this to happen again, to actually look at it, and I never did this. So that was something that threw me off. Yeah, and what I mentioned earlier, there's only so far you can go by profiling something in a way in which it will not be used ultimately, right? Because we knew this would end up being run as a server. And for a very long time, I was comparing like just timing or profiling results from the command line. But that's not what we do in production, right? So, so I think that's something to be aware of. But like if you look at profiles, if you profile, I also profiled, I didn't do it now, but I profiled during an A/B run, right? So if you run Apache Bench, so while it's serving all of these requests, I pulled CPU memory profiles, and you can do this by, I forgot how to do it. You can look it up. Basically, I think it requires a change in code, which will start a debugging server. And
Yes.
oh, hey, Nicola. Okay, I'm gonna mute. Okay. So that's super useful, because then you can like debug a live or profile a live system, right? So you can actually connect to this endpoint and attach a profiler. That was something super useful as well. And then you get more stable results, because you do it over many iterations, right? That's the reason why you then send 100 or 1,000 requests or whatever.
Thanks. Another question. Could you please a bit elaborate on amount of read system calls? I'm not very familiar with strace results. I mean, in terms of you mentioned that you've seen many reads, right? Many read system calls on the first iteration. Yep. So you even mentioned that you've seen more read calls than the files, or what did you mention? So could you please elaborate a bit on this? Did you expect, like, is it like each read call means reading the whole file, or reading the...
No.
Is it just IO operation, right? Just read any arbitrary amount of bits with whatever parameters we asked it to read.
Right. So this is the Golang reader interface. So it has a bunch of implementations, like limit reader, multi-reader, and so forth. So I'm not going to go through all of those. But basically, you ordinarily would tell it how many bytes you want to read, right? So we'll try to fill this array, and we'll tell you how many bytes it actually read, because maybe the source wasn't ready and hasn't already read parts of it. So it didn't fill the array. But essentially, you need to expect that, again, it depends on the sizing of the array as well, or the slice. But essentially, you need to expect that each of these will issue a system call, right, to instruct the kernel to produce data from this device so that your process can access it. So this is when your task will be suspended, and there's a context switch into, or I think called a mode switch, right, from user into kernel space, so that and your task waits for data to arrive, right? It's a synchronous call. It's not asynchronous. It's a blocking call. It's very expensive.
I just wonder, how many reads did you see on the first iteration, and how many reads are now? And
we looked at it earlier, right? We can
I wanted just to reiterate. And what is the threshold value you consider to be, extremely high number of reads or okay-ish number of reads? How do you judge?
There's it depends on the problem.
But
right?
how did you make the decision that there were too many reads? Just because it was on top of the list, or what?
No, that was the hint that there was something going on that probably shouldn't be going on. No, but like if you think about it, we have a bunch of files. Each file contains, I don't know how many files it was like 20 or something. And each file contains so and so many samples. They sum up to 32,000, I believe. So many thousand samples per file. So if you find that you issue as many or more reads than you have samples, then clearly that's inefficient, right? Because you could at least, at the very minimum, you could read a single file entirely into memory, so that you have all the samples in memory already. So
right.
That's kind of how I thought about it. So if we trace this, that's the old
But
version.
you would never have amount of reads less than amount of files, right? I mean, it's kind of makes sense.
Say it again. So
You would never get. Okay.
And 35,000 seeks. That's exactly the number of samples in, isn't it? I believe it is. So let's just do this. We don't want to do that.
So if you're reading the whole file now, do you have
It's
amount
not
of
exactly,
reads?
almost. but this is like, again, like it's, close enough. It's like these numbers are very close to the number of samples. So that was at least, these things can be red herrings, right? But it certainly looks like this is something where we do something expensive for each sample. And this is the time, right? This is not seconds or something. It's a percentage of the time spent, right? But 54% was spent in reads. I mean, obviously, this is something you look at, right? If you spend so much time cumulatively, but also relatively to what else is happening in a system call, that means your application isn't doing anything. It's just waiting, right, for the kernel to do something. That's
makes sense.
Something you want to look at.
Could you please show one last thing? Could you please show the strace data for the latest iteration of the parser? I mean, what is the current picture looks like?
Sure.
The same table.
Yeah,
I think this is very powerful, like an entry point to.
This is weird again, like this sig return. Yeah, please, anyone. See, now it's gone. I don't know what it is. It's something randomly happening in the background. I don't know.
So we have 22 calls.
Yeah, so this was 21 reads. That's actually pretty good.
So it's more or less similar to amount of files, right? We have, how many files do we have? Like
so that would be -1 because we have the.
How did you
total.
get the data set?
It's 34.
The data set you use to read files, where did you get it? Like from?
I asked Igor to pull it from a production Puma.
Nice.
Yeah. Hopefully we can do that ourselves soon. Yeah.
But why do we have reads less than amount of files? I mean, just a stupid question. Shouldn't we read at least each file once, or?
Yeah, that's a good question. I wonder if it's to do. Maybe it depends on what level in the operating system stack the read is issued. I'm a bit out of my depth here, but maybe it's because we interact, like Go interacts with the file system layer, right? But I could imagine maybe it's because if the file is in the buffer cache already, maybe it doesn't have to go through. If it's in the file system cache, then the file system layer can respond to that request immediately without going to kernel space.
That's quite possible.
That could be. Don't quote me on it though.
Okay, yeah, thanks. Yeah, that's all from me. It's an amazing demonstration. Yeah, thanks a lot.
Yeah, like it definitely goes up. See, like now it appears to be some, probably caching. It's not going down. All right, let's wrap it up here. Quite a bit over time. Let me stop recording.